Hoping everybody's hearing my voice, or otherwise, please write in the chat if something is going wrong. Okay, Paolo. Yes, of course, but I agree that that today's lecture is important, but even the saltwater content, I do believe it has some great importance because most of the efforts are on measuring saltwater content for a number of reasons. But anyhow, all the topics are important anyhow. Well, even though I have to say that today's lecture may be a bit heavy for some of you, but I do hope I can make it understandable, and of course use the chat or make comment if I was not clear on some points, and I'll try to repeat or to make things clearer. But I invite you to refresh your knowledge about basic physics and mathematics, just to appreciate more the today's lecture. So we will talk. 2 days ago we talked about. I introduced you the saltwater content, and that give us the idea of the amount of energy that we have in the system, in the soil, vegetation, atmosphere system. Today we will talk about the level of energy that water has in the system. So we start with saltwater potential, and I will be sometimes be very rude in a certain way, just with this preliminary slide saying that saltwater content does not predict how water moves into the system. This should be clear, and we can play with some exercise just to show that this statement is really true. Why? Because in the physics that we know, the physics that apply not only on our planet but in the entire universe, the physics are the forces that cause things to move, to speed up, to slow down, or change direction. So basically, as you know from the Newton's law, that forces cause acceleration. And if there is no force, okay, there is no movement, or if the velocity remains steady. On the other way around, if there is a net force that is applied to any object, even to the water molecule, the velocity will change and will induce an acceleration. This is basic physics. So this is why I told you at the beginning of my talk that you have to refresh your basic knowledge about physics and mathematics. So again, why do we need to refer to forces? So we need to refer to forces for the reasons that I said before, and but forces are vectors. So a force is vector and required to be uniquely defined. You need a triplet: the magnitude, the direction, and the sense of direction. And you can see the picture on the right of this slide that you know in that you from the manuals of physics. But there is the potential energy. Uh, mm, why we refer to the potential energy? Because first of all, there are some advantages. Because this is something that reflect the effect of a force. And from the modeling point of view, from the mathematics, it is not a vector, it's a scalar. So you can define the potential energy only if you use the magnitude. And potential energy allows us to analyze the conservative systems. Most of the problems where we deal with are conservative. We are lucky of that, and we can apply the laws of conservation of energy, of course, but force is still really important and necessary, even non-conservative system. An example of a non-conservative system is friction. So what we will mention in the next slides is we talk about the potential energy. Before introducing the potential energy, we should consider the variety of forces acting on a water molecule, and there is a variety of forces, and these forces act in different direction. First of all, we have the terrestrial gravitational field and the overburden loads that mostly act in a vertical direction. If you want an example of overburden loads, you can consider a house just put on a piece of land. This is an overburden loads. But every one of us and all the objects are subject in our planet to the gravitational fields. All of us are subject to gravity. But there are other forces, the attractive forces, because mainly the water molecules are polar molecules. And so there are some binding of the water to the solid matrix of soil. And then there is also something that happens at the interface between the liquid water and the gaseous phase, the air. And we will see what happened at the interface. This is very important, what happened at the interface between water and the atmosphere. But we are not dealing with distilled water, but we have some solutes that are in the water. So there are ions, and so there are some forces, attractive forces, that in most of cases oppose to the movement of water into the porous material. So just to be clear that this slide would like to show you that things are a bit complex when we deal with the soil, water, vegetation, atmosphere system. This continuum is a bit complex than the classic gravitational things that we usually consider. And this is why we prefer to leave the forces out of our concept, our modeling tools, because as I said before, the type of forces are different, and they act in different ways, and act on the water in different ways that is very difficult to describe. And this is why we prefer to refer to the potential energy. Why? Why in conservative system forces and potential energy that usually we mark with a U, a couple of U, are intrinsically linked. And I don't want to go into the mathematics of this, but the force, as you can see, is equal to minus the nabla U. Nabla is the derivative. So in a certain way, we can see in a very easy way that the force is the negative gradient of its potential energy. And even in this slide, you can see that I wrote this relation in terms of one direction, the vertical Z, the vertical direction, just to give you an idea of the scalar component of the forces. I remind you that forces is vector, and you have to define not only the triplet but also the different direction x, y, and z. So conservative forces like the gravity or a spring store an energy, this potential energy. Potential energy to do what? To make a work. And I just try to simplify this in this picture. You see, you have this black ball, and this ball is subject to gravity, to gravitational force. Then there is an external force that maintain this ball at a certain height with respect a reference, for example, your desk or your floor. So this means that if the external force disappear, the ball has the potential to make a work to move from the upper level to the lower level, and the H in this picture gives us the idea of the gravitational potential energy. I did this very simple example, and why? Because the gravitational potential is very easy to understand, and you know this from your previous studies at the grammar school, at the elementary school. You have the idea of the action of gravity. I hope this is clear, but as I said before, the forces that act in soil, vegetation, atmosphere system is a little bit more complex. This is why there is not only the gravitational force, the gravity, but even other forces generate a potential energy. Paolo, are you collecting a question? I hope that things are clear. I'm trying to do this. Not simple. This is not the right word, but I try to make these concepts understandable to everyone or most of you. So, because of the difficulties of describing this complex system of forces, as I mentioned before, that act in the soil, vegetation, atmosphere system, we refer to the mechanical energy. Why? Because the movement of water molecule in the system is the movement is so slow that we can disregard the velocity. So we can left the kinetic energy out of our most of our practical things in soil hydrology. There are other topic, for example, pumping groundwater issues and pumping that you cannot neglect the kinetic energy. So what we have is because of the forces that I mentioned before, we have a total potential energy, Psi with the T total, that we can, in a very practical way, to split in 4 components. We have the gravitational components that is linked to the position of the water in our flow domain. Then there is the metric potential due to capillarity and adsorption forces. We have the osmotic potential due to the solute effects, and it's very important for people dealing with plant physiology, for example, and the pressure potential that is due to the presence of pneumatic pressures. But we will discuss a little bit about each of these components. In this slide, I try to summarize the sign of this potential energy, because we will see that the gravitational potential and the pressure potential they both have a positive sign. The osmotic potential, due to the presence of a solute into the soil solution, in the soil water solution, is mildly negative. But the metric potential is negative, and the negative values can be even very, very relatively great. And we will see in which way. And I put in this slide some positive and negative, but positive and negative need a reference. So the reference state, and this is another agreement, an international agreement made by the International Soil Science Society. The standard reference state is pure water, free at atmospheric pressure and at a certain location in the system and a fixed temperature. For example, the atmospheric pressure in the location where you are dealing with, the temperature, the local temperature. But it's important that we consider the reference state as a pure free water, and this is assumed as the zero potential. So with respect to these definition, these zero potential, we have the gravitational potential and the pressure potential are positive, and the osmotic and the metric potential are negative. But this is only a sort of introduction, but I'm sure that we will discuss this later and hope things will be clear on that definitions. I think this slide is very informative, taken by the paper by Liu and other published in Vedus Journal in 2022. And I hope this is very informative. At least it was for me. We have the pure water. Oh, basically, look, we in these schemes, soil does not appear yet. So we have the pure water, so water, free water at atmospheric pressure at a certain location. And then we have a molecule at a certain distance, H0, from the floor. Then if you consider another bowl at a higher location, so the gravitational field just come into play and we have the gravitational potential. So the water molecule now they are subject to the effect of the gravity and the effect of the difference of the elevation between the molecule in this higher location comparing to the reference. So keep in mind that everything is referenced to the definition of the zero potential. But as I mentioned before, we are dealing with natural water, so there was water with solute and osmotic potential does come into play. But that should be also the possibility that there is the pressure, different pressure from the atmospheric, the standard atmospheric, an increase of pressure or decrease of pressure depends, and then you have the pressure potential. Oh, keep in mind, for example, that we also have an increase in pressure potential when you have amount of water that flow over the soil surface. For example, during runoff or flooding that produce a certain amount of water on the soil surface. So there is an increase of the external pressure that act on the water in the bowls. Let's go a little bit into more detail with the gravitational potential. So this potential is caused only by the difference in elevation of your molecule with respect to the reference point. And from the physical point of view, this gravitational potential is equivalent to a work that the molecule can do to move from in this case, from the upper location to the lower location. And I remind you that this potential is energy. Energy is equivalent to a work. We will see later that we can express, if we express this energy, we refer this gravitational energy to the unit weight of water. This is very useful. Why? Because you can just see this gravitational potential, because this gravitational potential is just equal to delta H. So the difference in the position between the two molecules, and I will show you later this in more detail. But keep this for that. But I think it's very useful to have an imaging of what the potential can be. And this is the, as I mentioned, the delta H. Delta H is the gravitational potential when you refer this energy to the unit weight of water. Hope this is clear, but it's very important because our brain need to see something, not something that is abstract, but just to not only to imagine this, but if you can see physical meaning, and the physical meaning of the actual meaning of the potential gravitational potential energy in terms of unit weight of water is just the difference in elevation between 2 points. Now we talk a little bit about the pressure potential, the hydrostatic potential, and you can refresh. I'm quite sure that you have talked about in your previous studies, the grammar school, I think, the high school, on the hydrostatics and the saltwater pressure potential. This potential represents the energy state due to the external pressure or because of the weight of water over a point. And I try to make an example just to simplify, to make this concept clear, I do hope. If we consider the differences in absolute pressure, P star, and relative pressure, just P. So if you have, for example, the sea level or a level in a lake, and you have the red dot on this dot on the molecule on that point, there is the action of the atmospheric pressure. But if you dive into the sea, you are just on a beach, and then you dive, you go into the sea, and you dive, and you get the yellow point 2. There is an increase of the absolute pressure. There is an increase of pressure, and these generate a pressure potential. And I put the relation. If you want to compute the absolute pressure on the yellow point in point 2, you have to sum the air pressure, the atmospheric pressure, to the weight of water from the red dot to the yellow dot. Is the multiplication of the water density of water, the G is the acceleration of gravity, times the H. H is the vertical distance between the 2 points. And I remind you that the product of the density of water by the acceleration of gravity is the weight, the specific weight of water. So you can also write this relation in terms of the pressure of atmosphere of air plus the multiplication of the specific gravity, the specific weight of water, and H. But you can express this, the pressure in the yellow dot, even in terms of relative pressure. Why we, in most of our practical application, we prefer to refer to the relative pressure, because all of us are embedded in the atmosphere. We all have the atmospheric pressure over our head. This is why we are interested in the increase or the decrease of pressure comparing to the atmospheric pressure. This is why we almost always we will refer to the relative pressure, and the relative pressure P2 in the yellow dot 2 is just the multiplication of the specific weight of water and H. I hope that this, even this is an analytical example, but I hope that this make clear 2 points, 2 things of this slide: the meaning of pressure potential and the meaning of relative pressure. Any question, Paolo? Everything is clear? I hope so.
Nunzio, so far so good, no questions.
Oh, they are astonished, or I don't know. Okay, okay, they are stuck on that. Okay, so I go on and go on, even try to make this concept even clearer, and we have the concept of pressure rate. Again, like in the case of the gravitational potential, our brain need to see something. So if we talk about the pressure potential, and I remind you that you measure the pressure in kilopascal, is Newton on a square meter, and but you don't see the pressure. But if we introduce the concept of a pressure head, we can see this pressure potential. And the pressure, if you divide the relative pressure by the denominator, there is the specific weight of water, you have H. And H is just the vertical distance between the red dot and the yellow dot. And you can see, if you dive 3 meters below the sea level, you have to add the weight of 3 meters of sea water. Okay. And so the concept is very easy. I hope it's very easy to understand, but the power of this concept is really, really important, because you can see the pressure potential. I hope even this slide make things clearer. And then we have the osmotic potential. The osmotic potential, I am sure that you are clever than me, smarter than me in chemistry, and you know that the presence of a solute into the bulk of water just generate some a movement of water, like in the picture. In this slide, you have a movement of water from the pure water to the saline water, and this movement means that not that this does not depend on water content, but depends on forces. This is a classic example that demonstrates that the movement depends on the forces. And so you have a movement from the left to the right, when there is the membrane. In this picture, there is a movement through the porous membrane, and you have a movement from left to your left, from your right to the saline water. And this is due to the osmotic potential. So there are some forces because of the presence of a solute, and these forces, only because the difference in a solute generate a potential. Which potential? The osmotic potential. Now I left at the end the metric potential, because I think it's requires some consideration. Any questions so far, Paolo? because I don't see
Oh,
the
so far
Q&A.
no questions.
Okay. So before introducing the matrix potential, just talk a little bit about the a very nice phenomenon that we have on our planet, the phenomenon of capillarity, and the fact that if you move a capillary tube in a bowl, you see that there is a rising of water into this capillary tube. And this is due to cohesive and adhesive forces that generate these things. Again, if you immerse, if you put this capillary tube, and then we will discuss what we should consider as a capillary tube. And if you put this in this bowl full of water, then there is a capillary rise. And try to calculate. We would like to calculate this capillary rise. This is very important in soil hydrology. This phenomenon of capillarity is due to I cannot go into some chemistry issues, but there are cohesion, and because of the polar nature of the water molecules, we have cohesion and adhesion of water, adhesion to the for example the wall or these leaves of the plant, but there is also a cohesion that because of the electrostatic charges in the water molecule that of course I'm making these concepts relatively simple, but I am sure that you are clever than me in chemistry and these things much more better than me. But this is an important phenomenon of the effect of cohesion forces. For example, we have a mosquito on a piece of water on a lake, or the raindrops on a leaf that just remain on the leaf because of cohesive forces. This happens for water, but I'm also sure that that for mercury the situation is completely different, because cohesion is much more strength than adhesion in a mercury liquid. Anyhow, but we're talking about water, and so we have both adhesion and cohesion forces are responsible of water movement from soil to the roots and into the plant. Everything is governed by the Young-Laplace equation. The Young-Laplace equation, and if you see on your left, there are two spheres and some water between the two spheres. We have two curvature. Water is entrapped in the spheres, and we have two curvature of water, and the radius of curvature is R1 and R2. And even in the photos, in the pictures below this graph, you see the amount of water as the energy become lower and lower. I remind you that minus 25,000 joule on kilogram is less than minus 1,500 joule kilogram. But we just to know, I don't want to leave this concept apart, but is important. And you can see that even when the amount of water became lower and lower, lower and lower into between the spheres, you have the meniscus, the curvature of water is greater, and this phenomenon is governed by the Young Laplace equation, and this means that there is a difference pressure between the non-wetting fluid. The non-wetting fluid is air, for example, and the wetting fluid is water. But of course, you have this situation even if you have oil and water, or if you have mercury and uh, and 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 uh, um, and water. And in this equation, I think from the picture is clear who are the R1 and R2, the radius of curvature of the meniscus, and you can also write this in terms of the average radius of curvature. But I want to just discuss a little bit the meaning of the term Hess. Hess is the surface tension. Measured in Newton over a meter, so is a force over length. And why this? This is a property. This is a property of water, or better, this is a property of the two fluids in contact. There is a surface tension between air and water. There is a surface tension between oil and water. Why? This surface tension comes into play because if we consider the bulk molecule, there is a sort of electrochemical equilibrium for all the molecules that are in the bulk of water. In this case, you can see the picture. But for the water molecules that are just on the surface of water, so there is a contact of water and air, there is these molecules are not in equilibrium because the air molecule have the electrochemical activity that is different from the water molecule. So for all the water molecule that are located just at the interface between air and water, we have a sort of discrepancy in a certain way if you consider this word, and rise a tension and a surface tension, because this is a tension that happens just at the interface between the non-miscible fluids. But I don't want to leave this in this way, but I prepared a sort of exercise, and I show you that we can demonstrate, even though we refer to a simplified situation, we can demonstrate the Young-Laplace equation. So let's consider everything okay, Paolo? No questions?
Yes, so far everything looks clear. No question.
Okay. So even you have no question, Paolo? Okay.
Not
Okay.
not yet.
Not yet. Okay, and then we will have a break after this exercise. Do you remember I made the animation of the putting a capillary tube into a bowl, into a bowl of water? Do you remember when you put this capillary tube into the bowl, there is a capillary rise. Then the exercise is that we want to compute these capillary rise. In the picture is the age. We want to compute age, and as soon as we put the capillary rise into the water, the adhesion of water just come into play. So you can see the meniscus. The water adhere. Water is a fluid that wet the floor. So you have the meniscus of water that adhere to the. Suppose that we have a glass. This capillary tube is made by glass, and more importantly, we have the water that enter into the tube and get a certain location higher than the standard location, and that is a meniscus. And again, the target of this exercise is that we want to compute the rise of the water in this capillary tube. So if we have equilibrium from physics, we know that if there is equilibrium, all the forces that act into the system should be equal to zero. And this is what you see in the upper part of this slide. We have the summation of the forces, all the forces, in the vector forces. But of course, if we consider the vertical component of all the forces, even the summation of the vertical forces must be equal to zero. So just compute these forces. What we have the atmospheric pressure. You see, is this sort of green arrow. The green arrow acting from top to down is the atmospheric pressure. And if we know the atmospheric pressure P atm, the forces is equal to the multiplication of the pressure by the surface, because I remind you that pressure is forces over an area, and the area is the shell, the spherical shell. So is P Greek d square over 4. And I remind you that we have to be consistent in this exercise, in the sense that we have to compute the forces, all the forces. Pressure is not a force. Pressure is a force divided by an area. So the atmospheric pressure is that one, and we also consider a sort of agreement that we consider negative the vertical forces that act downward, and the atmospheric pressure, the green arrow act downward. So this is why I put a minus signal sign. Then we have another pressure, a pressure just below the meniscus. So the atmospheric pressure acts over the meniscus, but there is the pressure just below the meniscus. And I call this F star. and this is what we would like to compute. So this arrow is still vertical, but acts in upward. So there is a plus sign. So and we have to multiply p star by the area. So pi Greek d square over 4. This is not enough. Why? Because this meniscus just appear because of the surface tension, and the surface tension you can see in the scheme in the left below. There are some forces that are located in the perimeter of the spherical cell, and we can and this is highlighted by this ellipse here. We have to consider even these forces and the tension, the forces due to the surface tension Ts is still positive because all the forces are in the vertical direction are upward, and the perimeter of the shell is pi Greek by d, and we have to consider the cosine of the angle that the spherical cell have with the tube, the capillary tube. So we have computed, I hope that things are clear. We have computed the three forces, the atmospheric forces, the forces due to the pressure just below the meniscus, and then the forces due to the surface tension. And in this slide, I put all these all together again. And what we have, we can just use the summation equal to 0, and we can put the positive forces on the left and the negative force on the right, and then so the only the things that we don't know in this equation is p star. So what we can obtain from this equation is the value of the pressure P star just below the meniscus into the capillary tube. And this is the the relation we have. So P star is the pressure of the atmosphere, P atom, the pressure of the atmosphere minus 4 S is the surface tension, the cosine of the angle theta or alpha, that doesn't matter, and the diameter. Now I made a question: what does this equation tell us? Can someone can help me to understand this equation? What this equation really tell us? This is a very important. It's very simple. It's very simple relationship that give us the value of the pressure just below the water meniscus, and we know everything. We know the atmospheric pressure, we know the diameter of the capillary tube, we know the surface tension. If we open a chemistry book, we can find the surface tension between air and water. But from the practical point of view, what does this equation tell us? Is someone can help me to reply to this question? Paolo, there are
there is is that the pressure is lower than the atmospheric one? That's one question.
No, this is a Of course, the a part of the question, but this is the right answer. This is this equation is very simple, and I show you that we can obtain this equation in a very simple way, just making an equilibrium of forces. But as someone mentioned, it is important to understand that the pressure P star just below the meniscus is lower than the atmospheric pressure. Why? Because the 4 is a number, is positive. S is surface tension, is a property and is positive. The cosine vary from 0 and 1, so it's positive. And D, the diameter, is positive. So the entire ratio on the right is positive, but there is a negative sign. So this equation tells us that the pressure just below 1 millimeter below the water meniscus is below the atmosphere pressure. So this means that there is a suction. So this is why this gives us the idea that like we when we soak Coca-Cola from a glass water from a glass Coca-Cola or whatever, and you make with your mouth you make a suction just to have the Coca-Cola or the Coke or the water moving to your mouth. You with your mouth you generate a suction, and this is what happened in a capillary tube. There is a suction because of the cohesion of and the adhesive and cohesion forces, and because of this very small diameter of the capillary tube, these generate a negative pressure, a pressure below the atmosphere. So this pressure generate a capillary rise. So just to recap, we have the P star, the pressure, the red arrow generate a pressure just below the meniscus, and we can also simplify even more this equation because in terms of relative pressure, as I mentioned before, the atmospheric pressure is set at 0, and usually if we have the glass of the capillary tube is made by glass, the angle is close to 0, so cosine of 0 is 1, and the pressure, the relative pressure below the meniscus is just minus 4s over d. And so I think that even from the analytical point of view, you can understand that the capillary pressure are negative. And I also introduced the pressure head, so you can transform this pressure in terms of a pressure head if you consider the specific weight of water. So the last relationship in below this slide give you the analytical way to compute the capillary rise. And this is very interesting because you see that 2 is just a coefficient, 2 is a number, S is something fixed by the fact that you have at the interface air and water. The specific weight of water is something that is fixed, so the capillary head, the H, the capillary rise, depends only on the radius of the capillary tube. And I show you here this, if we have a a capillary tube of 560 micron, you have a capillary rise of about 5 centimeter. If you have a capillary tube of 100 micron, you have a capillary rise of 30 centimeter. And if you have a capillary tube of only 30 micron, you have a capillary rise of about 1 meter. Just to give you the idea of how small are the pores in the soil, and we can also have capillary rise even more than 1 meter. But just to give you an idea, and you can put this in an Excel file, and you can compute. This is the surface tension between air and water is 0.073 Newton per meter, and you can compute in a very easily way the capillary rise in terms of the diameter of the capillary tube. Okay, I think that we need a break. Let's say 10 minutes break, Paolo, or
Yes, absolutely. Even 15 minutes to Nunzio, there is only a question before the break.
Yes. Yes, please.
In capillary rise, the water pressure is minor than atmospheric pressure, so it causes surface tension, pushing water toward the low pressure zone.
I don't know if I understood well this question, but the fact that we have a pressure that is below the atmosphere pressure means that there is the tube, the capillary tube, serve as a suction. So this is why the water rise into the tube, even though because the cohesion also, and this is why there is the curvature of the meniscus. I don't know if I understood well the question, but the meniscus is just to compensate the non-equilibrium between the atmospheric pressure and the pressure P star just below the water meniscus. I don't know if I replied the question, but the fact that this is negative give you an idea of the suction, and this is why I made the example when you want to drink a beverage from a glass and using a straw, and you have to, with your mouth, you have to generate a suction. Only if you generate a suction, you can go against the gravity. This is another point. I try to make this point even clearer. I want to be very clear on that you should consider that the water is flowing into the capillary tube from the lower level to the higher level against the gravity. And why you can go against the gravity? But because the cohesive forces that generate this kind of suction, and this kind of suction is able to move water from the lower level to the upper level. Otherwise, this is not possible. The only way that you can move water from a lower level to an upper level, you need a pump. In this case, the pump is the characteristic of the polar water of the cohesive and adhesive forces that generate a suction. I don't know if I reply to, if I answered the questions, Paolo.
Yes, it's from Anaita. So let us know if okay. Said yes. Okay.
Okay. Good. Okay. We reconvene at 2:30, 15 minutes break.
Okay, okay, 15 minutes is fine. Thank
If
you.
we, okay.
2:30 p.m. Until you can start again.
Okay, I hope again, Paolo, let me know if you hear me and if the screen
Yes.
is on. Well, okay. I hope that the exercise is a classic hydrostatic exercise. It's just a classic exercise that help you to understand how the forces act. And again, I also see from the chat, I hope that things are even clear if you consider the fact as written in the lower part of this slide, that we consider the relative pressure. So this means that we can set the atmospheric pressure at 0. That means that the P star, the relative pressure below the meniscus, is negative. But I want to be clear on that point because I want to remind you that do you see the arrows, the green, this kind of a green arrows? This is the atmospheric pressure, and the atmospheric pressure just act even on the level of the ball. This black line is the isobaric line, so the line where all the pressure are the same. I hope you have this concept clear. This black line is the line where the pressure is the same over this line. And which pressure? The atmospheric pressure. So the pressure is 0 here, but in the red point just below the meniscus, the pressure is negative. There is a suction, and this is why the water can move from the lower level to the upper level into the tube. And this is the phenomenon of capillary rise. I hope things are. I made just now this animation trying to make things clearer on that point. This is if you just refresh your knowledge of physics, this black line, again, I want to repeat many times, this black line is isobaric line. Isobaric means that the pressure over this horizontal line is always in any point is the same. Which pressure? The atmospheric pressure, because we have the green arrow that produce the atmospheric pressure, like the atmospheric pressure over the meniscus, but the pressure just 1 millimeter, 1 micron below the meniscus is negative, and these generate a suction. In the same way you make a suction with your mouth when you want to drink the Coke from the glass using a straw. I hope this analogy makes sense for you. Any question, Paolo, from the audience?
No, not so far.
Okay, but I told you this afternoon the lecture is a bit can be a bit heavy for you, but if you refresh your knowledge about physics, this is very simple physics, and this is an exercise. It's a very simple exercise using the equilibrium of forces and nothing more. Okay, let's go now into the soil situation. And you can see the analogy. If you have a vessel, a bowl full of water with different capillary tube, you have different capillary rise. And this is a model of the soil pore, the capillary tubes with different diameters are not only are only a sort of analog model of the porosity of the soil system. And you have small pores, you have larger pores, and you have a higher capillary rise in a small capillary tube. So you have the capillary rise, higher capillary rise in the in smaller pores. And this phenomenon is regulated by the Young-Laplace equation, and I have shown you in the exercise we made before that you are able to obtain the Young-Laplace equation in the very simple but very informative exercise and a very informative example of a very classic capillary tube, a tube with a constant diameter or a constant radius r, and depending on the diameter of the radius of this capillary tube, you have different capillary rise. Which
Nunzio,
capillary line? Yes.
sorry, there is a question from
Yes.
Xavier. Has the depth of the bottom of the capillary tube in the liquid an importance on the rise?
No. There is no importance. Of course, there is no importance. It's just of course you have to be sure that water can enter into the tube, but it's not but at the same time, if you put just the tube just you put just on the liquid surface, the cohesive forces cannot act in a very good way. So of course you have to put to insert the tube for at least a couple of centimeters at least into the bowl. Any other questions?
No.
Okay. So what is important from the soil hydrology point of view is the take-home message that I write just below on the right of this slide. Smaller pores are able to retain water with greater energy. Again, we attach an energy meaning, an energy potential meaning to the phenomenon of capillary rise. This is important, and I hope that this analogy gives you an idea that if you have clay soils that usually is made up by a large amount of smaller pore, clay materials, clay soils retain more water comparing to sandy soil. If you have the beach soil, of course, you just lose soil very easily. Why? Because sandy soil have large pores, a greater amount of large pores, and they have less ability to retain water. Hope that this is clear. Hope also what is clear, what I would like that you obtain from this talk is the analogy, the physical analogy, and the practical and the analogy that the the physical meaning of the capillary pressure, but the practical meaning of retaining or releasing water depending on the cohesive force of water and the dimension of the pores. And again, you should also keep in mind that the soil is has a very complex porosity. So this complexity make the retaining of water a very complex thing. I hope this slide just clarify what I'm saying, but again, I show you again in a simple way. Just consider a very simple model. The simple model is to consider that the soil is made up by a bundle of capillary tube. This is the classic, very simple soil model. You model the soil porosity as a bundle of capillary tube. And if you have a tube with a diameter of 560 micron, you have a very low capillary rise, only 5 centimeter, as you can see from the picture on the right. But smaller diameter, 100 micron, give us a capillary rise of 30 centimeter. But if you want to see the diameter associated to about 1 meter of capillary rise, you should consider a diameter of at least 30 micron. Okay. And in the actual in real soil condition, you have a diameter even smaller than 30 micron. So this is why you can have a capillary rise above a groundwater even more than 1 meter, even 5, even 10 meters. You have you can get a capillary rise above the groundwater level, even more than 5, 10 meters. And then with this very simple exercise, now you can understand the relationship between the capillary rise and the porosity of the soil you are dealing with. Then, if there are no questions, just I move to something that I already mentioned before, but now I want to be more specific. And the total water potential has the component of gravitational, matrix potential, osmotic potential, and pressure potential, but the dimension unit depends on if we should refer to a unit of pure water. Do you remember the definition of reference? But the reference can be a mass of water, or the volume of water, or the weight of water. And I also anticipate in one of my previous slides that is very, from the practical, from the technical point of view, it is very easy and understandable to refer the soil water potential to the weight of water, and I show you why. But let's start with referring the water potential to the mass of water. So the potential energy has the dimension of the square of length or the square of time, and the units are the joule on kilogram. I remind you that the potential energy is a work, and work in the system, the international system of units is the measurement is joule, and the mass are kilogram. And so in terms, the saltwater potential in terms of mass is measured in joule or over kilogram. But usually in soil hydrology, we don't use too much this. This is using in thermodynamics or in chemistry. The chemistry people, they prefer to use the joule on kilogram, and of course, because mass cannot change. Only be transformed. The Lavoisier principle. So this is why the chemistry people they refer to the mass. But from the technical, practical point of view, it's very interesting what happens if we associate the saltwater potential to the volume of water. Why? Because we are dealing with water, and water is a very specific type of fluid. Water is a fluid quite incompressible, means that the volume has only small changes, of course, in a practical situation. So if we divide the water potential in terms of volume, we have the energy potential that is expressed in terms of Newton on square meter, that is the pressure. So the potential energy referred to the volume of water is a pressure. This again gives us the idea of the meaning, the physical meaning, the practical meaning of the pressure. The pressure is the water potential referred to the volume of the unit volume of water instead of the unit mass of water. And this is also a way that you can understand more the meaning of the physical and practical meaning of pressure, and what is the meaning of pressure in terms of soil in the realm, in the world of soil hydrology. But in most of the cases, we prefer, since even the volume does not change, but even the weight of water does not change too much, again, at least into the most of the practical application. So when we refer the potential energy to the unit weight of water, we have the dimension of the length. So the unit is in meter. So and this is very easy to understand. And I made the exercise with you when we talked about the hydrostatic pressure. Do you remember the hydrostatic pressure or the gravitational potential? We mentioned about the elevation of something above a certain, or below, of course, a certain level. So this elevation is nothing more than a measure of the energy potential. And in most of the manuals, in most of the textbook that you find in soil hydrology and soil physics, usually they use the same terms. The phi is the total potential energy in terms of weight of water. And by neglecting the osmotic and the pressure potential, we have the total potential phi is equal to the sum of the gravitational potential. What is the gravitational potential? Is the elevation, Z. Z is the elevation with respect to the reference. For example, your elevation comparing to the mean sea level. No, you see in topography the elevation, the position comparing to the mean sea level. So, but this is a form of energy. Which energy? The gravitational energy, the gravitational potential energy, and then the metric potential, the capillary potential, is expressed in terms of age, and is the metric potential. And I am sure that on Monday, Paolo will introduce this total potential in the modeling of soil water flow in the soil vegetation system using this equation for the total water potential. Total water potential is sum of the gravitational potential Z and the metric potential H, but in terms of unit weight of water. Any questions before going to how to measure the pressure and the metric potential?
No questions.
No questions. Good. Hope things are clear. But I told you that the today's lecture could be a bit heavy, even for me as a speaker, comparing to the previous one. Anyhow, let's move to the how to measure the pressure potential. So the pressure potential can be measured in a very easy way. With the piezometer. The piezometer is just a tube. You make an excavation. You put a plastic tube or a metallic tube just to get the groundwater, and then you can use this steel tape with a bell sounder at the lower hand. When the sounder just get the water, then the bell sounds, and you know that you get the water below the soil surface. Of course, this piezometer in the lower part should have some holes, so the water of groundwater can enter into this tube. This tube is called the tensiometer or phreatrometer because this kind of groundwater is called the phreatic aquifer or unconfined aquifer. You can have the water table below the soil surface, and the horizontal line is the separation between air and water. So this means that the horizontal interface that you see on the water table is the horizontal isobaric plane, the plane where the relative pressure is zero. The plane where the atmospheric pressure just act on this interface, and in terms of relative pressure, this is the horizontal plane with zero pressure potential. And then you have, if your point of interest, the red point, is below this water table, you can, in a very easy way, just to compute using the hydrostatic relation I showed you before, you can compute the pressure potential in the red point.
Nunzio,
but yes.
There is a question on the previous slide. Is temperature negligible when considering water potential in terms of unit volume?
Actually not, of course. I will show you that we also have neglect the osmotic, but for practical application, the temperature is considered quite a fixed value. But if your specific problem, just should account for different, very different temperature level. Then, of course, you have to account the effect of temperature, where the temperature affect the surface tension. The surface tension can be affected by the temperature, and other properties also are affected by temperature. But again, it depends on as I mentioned in my previous lecture, it depends on the uncertainty. If you are able to quantify the effect of temperature on your variables, okay, just account for them. Otherwise, you should keep in mind that there are more uncertainty if the temperature effect play a certain role, but you are not able to quantify this effect. I don't know. I hope I answered this interesting, and I thank you for this important question.
Yes, no more feedback. You can go.
Okay. Okay, and hope even the measurement of the pressure potential, the positive pressure potential is clear. We should instead make some analysis of what happens when we want to measure the matrix potential, the matrix pressure head, what I call the suction. So we want to measure the pressure of the water into the soil pores. And this is a question. So, and I try to make an animation and hope you appreciate this animation. We have land with the trees, with animals and everything. And we have unsaturated soil. We have a soil with a certain, not saturated, so not all the pores are full of water. This is the definition of unsaturated zone. Unsaturated soil is the soil where not all the pores are full of water. The case of the groundwater. The groundwater is the case of all the pores of the soil are completely filled by water. But now the question is, what happened? How can we measure the pressure potential that we have called the matrix potential of water into the soil? So we can do a very simple exercise. We can again, like we have done here, we can excavate and then insert a tube, not a capillary tube, of course, a piezometer. We can put a piezometer into the soil until we get the unsaturated zone. Has someone knows what happened if we put water into this tube? Someone can help me to understand what happened if I put water into this tube, like in this animation. Does somebody?
Yeah, Felipe says water will come out.
Why? Come out is I prefer it to be more precise. Why water, as Felipe said, goes down?
He says by capillary forces.
No, this is not the case. This is not the right answer. So again, I put a piezometer, for example, a tube of 20 or 30 centimeter in diameter.
There
Then
are other
I
two attempts. Kamat says the sub-atmospheric unsaturated zone will suck in the water, and Isai says the water will flow inside, like infiltration.
but this is not the answer I expected. Again, if we there is no infiltration, or actually the infiltration is in the soil, but I'm talking about the water into the tube. And if I make this kind of experiment, I see that water very, very abruptly, very, very soon, the water just goes down and go into the soil, disperse into the soil, and then water. And there is a sort of hint in this picture, and I hope that someone get this hint. So again, somebody. Can somebody help me to understand why water just very soon, very abruptly, the water is dispersed into the soil? No answer? Paolo? No answer?
Walter says nothing happens. We haven't reached the saturated zone. Pietro says water exchanges with the air in the pores. Felipe says atmospheric pressure difference. David says negative pressure will
Okay.
suck the water in.
Okay, Felipe, you are close, but you didn't win. Is your answer is close to the actual answer, but it's not the perfect answer. I try to give you the perfect the what actually happened, and again you should consider the equilibrium of forces. When you put water, you have the atmospheric pressure. You see the PA, PATM, PA, the black arrow. Not only this, but at the bottom of the piezometer, you have in the piezometer this weight of water. And so at the bottom of this piezometer, you not only have the atmospheric pressure, but you have the weight of this column of water. So everything is positive into the tube. And what is the sign of the pressure into the soil? The soil is under suction. The soil, the water, the metric pressure is negative. So negative is less than positive, and this is why you lose water very, very abruptly. Again, you should keep in mind the equilibrium of forces. You have the pressure the atmospheric pressure on the top of the piezometer. Then you have the entire column of water. So the weight of water is really big, but you have a negative pressure into the soil. So the positive pressure just prevails, is greater than negative. Positive is greater than negative, and you lose water. Hope things are clear now in this very simple experiment. This means that you cannot use the piezometer to measure the suction into the unsaturated soil. Any question? Everything now is clear. I hope.
Yeah, there was the last comment by Walter. The tube is full of water, so the water goes from high potential to low potential.
Right, right. Everything move from high total potential. Please.
And another question is from Amor. How about in confined aquifer?
No, this is not. No, the aquifer is just below, where the soil is just up over the water table. So we are not dealing with the aquifer. But you can see here for the aquifer you have the piezometer. Again, if I was not clear, you have the piezometer is a cylinder, is a PVC cylinder or metallic cylinder, steel cylinder. The cylinder is only with the holes only in the bottom, so the water can enter into the cylinder, and because of the hydrostatic pressure, the water into the piezometer is the same level of the in the phreatic aquifer, in the unconfined aquifer. Now we are dealing what happened in the soil, not in the aquifer, and we would like to measure the pressure that water has in the soil, and the aquifer is below, so it's then maybe the water that I put into piezometer of course goes to the aquifer, but it is good the comment that or I want to adjust a little bit the comment. Please consider that everything moves from the higher total potential to the lower total potential. So this means that you not only have to look at the position, means the gravitational potential, but you also have to look at the gradient, the difference in the metric potential, if you want to see how water moves into the soil system and the soil toward the roots of the vegetation. So, any other questions? I know that all this is maybe something strange to some of you, but believe me, if you start thinking about on using the equilibrium of forces, if you start thinking about that everything move to the total, from the higher total potential to the lower total potential, things, as I show you later, are clear even in the movement of water from the soil to the vegetation and to the atmosphere. But I would like to know if this important point is clear. This is another way to understand the how the energy potential is very useful and make us to understand, and in a relatively easier way, how the water moves in a complex system like soil, vegetation, and atmosphere like soil hydrology does. Paolo, any other question? I cannot see the Q&A or other things.
No more questions. Just a comment, but no more questions.
Okay, so and how we solve this problem? The problem was solved by Richards and Gardner, that in 1936 they invented in a certain way the tensiometer. The tensiometer means is not a piezometer. The piezometer measures positive or zero pressures. The tensiometer is able to measure something that is under tension, means in a suction. And to do this, you have to use, yes, the piezometer. You see, this is the original piezometer with the tensiometer. Of course, this is the tube full of water, and at that time there was the mercury that measured the pressure, but now you cannot, because by law you cannot measure the pressure using the mercury. So now you have to use different things, and but the important thing is to use a porous cap. The porous cap is a cap with very small pores that allow water to flow from the tube to the soil, but not air. So only the water just goes in equilibrium with the water into the soil, and when there is the equilibrium, this system is able to measure the suction. And I cannot go into more details because maybe if we, Paolo, we make some of you can join our lab, and so things are more understandable. But I hope this slide can make things clearer. So again, if you use only a tube that is open in the lower part, water into the tube just flow out very rapidly. Why? Again, because the water into the tube has a positive pressure, while the water into the soil has a negative. So the water goes down very abruptly. But if you use, like you can see in the enlargement in the picture on your right, you see the porous cap. The porosity of this cap is so the porosity is so small that this connect the water into the tube to the water into the soil, but air cannot flow through the porosity. So when there is the equilibrium, this system just measures the suction, the metric pressure that water has into the soil. Maybe there could be some question. I hope things are clear, but things becomes really clear if you join a lab or you in your lab you have something like that. But my wish is that you understand the basic principle of functioning of this equipment. Again, the idea is to use a porous cap at the bottom of the tube, and in this way the very small porosity of this cap is able that air cannot flow through the porosity of the cap, but the water into the tube became in equilibrium with water into the soil, and after a few minutes or a couple of minutes, there is an equilibrium of the water into the tube and the water into the soil, and the vacuum gauge can measure the negative pressure that the water has into the soil. Are there any questions, Paolo?
No.
Okay. Okay, and so let's also, it's important for people dealing with.
Sorry.
Yes.
Sorry, just one quick question. Is this same principle of pressure plate? How do they differ in terms of accuracy?
Of course, yes, the principle is the same, but the accuracy depends in both equipment by the porosity. So the accuracy depends on the porosity of the cup, like in the pressure plate depends on the porosity of the membrane. So the mostly the porosity just to give you the possibility to measure higher suctions, of course, but the type of porosity, the type of a cup, and the type of a membrane just also affect the measurement. I hope I answered this interesting question.
Okay.
Okay. So, and again, in soil hydrology, it's also important to not only to have the analytical equation, but also to get familiar with the values. So, in this slide, I remind you that some basic things. 1 atmosphere, on average, is about 1,325 kilopascal. That means is the well-known 760 millimeter of mercury. That is equivalent also to 1,020 centimeter of water. This is in the standard of the atmospheric pressure, but in most cases we prefer to refer to the bar. 1 bar is 100 kilopascal. So there is in practical application does not make any real sense to have all these other decimals or digits. So usually we refer to the atmospheric pressure in terms of bar. So 1 bar is the equivalent of 100 kilopascal. And I also put the equivalence. So if we have a pressure of 300 centimeter of water, means negative suction of minus 0.3 bar or minus 30 kilopascal. 1,000 centimeter is 1 bar. So it's the famous 10 meter of water is minus 1 bar, is minus 100 kilopascal. And then at the end, we have the very famous, I know for those of you who are agronomists, you always talk about the minus 15 bar. Is the famous permanent wilting point. The minus 15 bar is equivalent of 15,000 centimeter of water or minus 1,500 kilopascal. And I hope this also help you to understand more the differences between the system of units.
And not to mention the field capacity there.
No, you know, Paolo, I am always against the field capacity. Just I'm a little bit more confident with the permanent wilting point, but I cannot talk about the field capacity. It is something that make me crazy. So, and people that knows my papers on field capacity, they knows. So this is why I cannot put the field capacity point. But there are any question on it, or is your comment, Paolo?
No, it was my comment. Maybe we can dedicate a webinar on field capacity. Oh, Felipe, field capacity is quite tricky to work with. Oh, please explain why. Oh my God, I raised interest on field capacity.
Oh no!
And it's a long story.
Manage.
Maybe we can dedicate.
No, I cannot. I cannot manage this because it's too a risk. If I fall in this discussion, we open a debate.
The Pandora
The
debate.
Pandora. But an interesting thing, Paolo, is that you can also collect some wish from the audience, and maybe we can in the future we can make some specific talk on some specific topic. For example, the topic of field capacity and permanent wilting point. Of course, I would be very happy, but we have to dedicate at least 1 hour or 1 hour and a half to this point.
Yeah, because there are 3 or 4 questions on field capacity, so it's better to to dedicate.
Okay.
It's too long.
No, no, no. It's impossible. But again, if you can send an email to me and Paolo, and I'm sure we will be very happy to discuss with all of you. But the discussion on field capacity and permanent wilting point, this the discussion on the available water for plant growth. This is the topic, is very interesting, and from my point of view, I will be very interested in not only to discuss with you, but and to put forward my thought, but I also like to have your ideas and this it will be not a real seminar, but something that we exchange ideas and experiences. Okay, anyhow, let's get back to our any other comments. I hope no on field capacity.
Okay. There is a comment from a question from Pietro. Going back to the ceramic cup, could you please
Yes.
repeat why air does not exchange, but water
Yes,
does?
yes. The everything is managed by the porosity of the cup. So actually, we should be more precise. It's not the air is change, but the air, because if you see this enlargement, can you see my pointer? Into the pore of the porous cup, there are the meniscus of water, and this meniscus prevent the air to go through from the tube to the soil. So only the water into the porous of the cup. This water is connect the water in the tube and the water into the soil. If I can, Paolo, it's the same here. It's the same in this exercise. You see the meniscus. The meniscus prevent the atmospheric the atmospheric pressure to go into the water bowl. So it's like someone that prevent the air to enter into the capillary tube. I don't know if this is clear. This is very important. The cohesive force and the surface tension just prevent water to enter into the capillary tube, and there is the force are so strong that instead of preventing air, there is a capillary rise. So the surface tension and the cohesive forces are stronger than the atmospheric pressure, that there is a rise of the water into the capillary. I don't know, Paolo, if I make this even help me just to understand if I make the right comment, because this picture just give you an idea that the the meniscus of water prevent the air to be connected to the rest of the tube. And this is what happened here. You should consider that in the porosity, in the small porous of the cup, there is the same. There are some meniscus, and this meniscus allow the water to be connected from the tube to the soil, but water, the air cannot enter into the system.
Yes, it's clear now.
Only when the meniscus breaks, because when this is an important point. I think for this question, because of course when the soil become drier and drier, of course the meniscus become even the curvature of the meniscus become even higher, but at a certain point, the pressure of air is so strong that the meniscus is broken. And so the water of the tube because of the air pressure just goes into the soil, and so the tensiometer does not work any longer. I hope that this could be clear.
Nunzio, last question, sorry.
Yes.
Is the tensiometer an indirect mean to measure the porosity of the soil on site through the water potential?
Oh, in a certain way, yes, because there is this tensiometer, like in this slide, you can see different kind of tensiometer. You have on your left, you have a laboratory tensiometer, a mini tensiometer, and in the center and on the right of this slide, you have the field tensiometer, the tensiometer that you can use directly in the field. Is a sort of indirect in a certain way, because you make a sort of a connection between the water into the tube and water into the soil. But now, thank you for this question, because actually you measure you consider the curvature of the meniscus, and you consider this curvature and this the capillarity effect that is linked to the metric potential. And of course there is a sort of a connection, and there is a sort of indirect measurement. So is something in between. I hope that I answered these interesting questions.
Okay.
If there are no more questions, just very quickly, you can see different kind of tensiometers, and one disadvantage of this kind of tensiometer that you have when the soil becomes drier and drier, you have the water into the tube become lower and lower, and at a certain point you lose all the water into the tube. So you have to refill the tensiometer in a certain way if you wish that the tensiometer goes on working. This is why on the extreme right of this slide you can see a new type of tensiometer, even though this is very expensive, that make a sort of automatic refilling of water, in the sense that when the water into the tube becomes lower than a certain threshold, automatically there is a sort of small reservoir. There is a refilling of water into the tensiometer. Another disadvantage can be that you don't have the electronic measurement. At least, again, the picture on your right also has this digital measurement, but again, this tensiometer is quite expensive. But if you use the classic tensiometer, you see there is a vacuum gauge, vacuum because you measure negative pressure, but this is something that you have to go into the field and to read the suction, the negative pressure. So you don't have a digital measurement, a continuous measurement of the suction, and of course, especially for in certain application, this can be not a good thing, and you prefer to have a continuous measurement. And here you have the Teros 21 from meter, but there are even other. I put this because we have this in our observatory, and this equipment works very well. But again, this is a real indirect measurement of suction head, because the water potential, the matrix potential measured by this is actually not directly measured, but this ceramic material measure the water content using, again, as you can see, the dielectric permittivity. This is why it's very important for you, the previous lecture that we had 2 days ago about the dielectric permittivity, because most of the soil sensors make measurement relying on the measurement of dielectric permittivity. But this sensor actually measure the ceramic water content, and then using an internal conversion, there is a conversion of the water content in matrix potential, using, of course, a calibration curve, but this calibration curve is specific of this ceramic material, so the calibration curve is produced by the factory. So the factory gives you the calibration curve, or more precisely, I have to be more precise. The factory gives you already the value of the matrix potential. So, and you can see it's a very easy to use, because there is an electronic device. You have a data logger. You can put this sensor, connect this sensor to a data logger, and you have the measurement of matrix potential. And I listed here, you can read the key functional principle of this equipment. And this is an evolution, or you can find in some old textbook the gypsum sensor, and this is the evolution, the modern evolution of the old gypsum sensors that measure the matrix potential. And in this slide, you see the an example. We, in our observatory that I showed you last time, we have these sensors located at 3 different soil depths, and you see the measurement of matrix potential, and you can appreciate that, of course, when there is a rainy period, for example, in December 1917, this sensor measure a value of matrix potential close to zero, so the soil is almost saturated. But in the period in the spring or in some during summer, you have that the soil becomes drier and drier, so you have the matrix potential that become lower and lower in terms of matrix potential, or in terms of suction you have an increase of suction from 2,000 kilopascal up to 4,000 kilopascal. So drier and drier soil because of the dry period. One comment is about the measurement range, because this kind of equipment, even though I understand that the factory are improving this, but this sensor is unable to measure the matrix potential in the wet part when the soil is relatively wet. Actually, the sensors start measuring the suction from 9 kilopascal, about 1 meter, 1 meter of water into the soil. But the advantage that you can measure the matrix potential, the matrix pressure up to 1,000 bar, and this is very, so is 10 to 5 kilopascal, and this could be very helpful in very dry environment. But again, there is the limitation that this kind of a sensor cannot measure the suction head under very wet condition. But of course, as always happen, we cannot obtain everything from a sensor. But so this is something, a price that we can pay, using instead the advantage that we have a digital measurement, an electronic flow of data using a simple data logger. And now I close this first part of the seminar, just showing you the importance to consider the difference in total water potential to understand how water flows in the soil, vegetation, atmosphere system. These are very common picture that you can see in the textbook of plant physiology, that even in the last couple of decades now, even physiologists also understood the importance to consider the differences in total soil water potential, to understand how water moves from the soil to the root, from the root into the plant, to the leaves, and out to the atmosphere. We have on average, for example, this is only an example, the average total potential in the soil is minus 0.3 megapascal. So the roots should generate a lower pressure. So minus 0.6 is lower than minus 0.3. Be careful. So this is why this difference in total soil water potential, total means that we should also add the gravitational potential and into the root the osmotic potential. But this is the only way for water to move from the soil to the root, to enter into the root, to go against the resistance of the tissue of the roots to go into the roots and then move to from the roots to the trunk. And again, be careful. Minus 0.8 megapascal is lower than minus 0.6 megapascal in total water potential. So this is why water goes against gravity and move upward to the leaves and then transpirate to the atmosphere that on average is about minus 0.5 or 100 megapascals. Any questions?
Nunzio, just one, I think it's referred to the sensor, Teros 21, I think it's from Walter. I heard that it's not possible to measure less than PF of 3, but I don't understand why.
No, there is the way this sensor measure the matrix potential. Again, this is a ceramic, so it depends on the material and depends on the porosity of these materials. And so this means that the factory warn you that the measurement. So just to be clear, in a certain way from the theoretical point of view, you can transfer the information from the ceramic water content to the matrix potential from the theoretical point of view. The factory is warning that the uncertainty in the wet part of the system is so high that the measurement is not reliable. So this is why depends on the factory, depends on the sensor. For example, for Teros 21, the factory assures that the measurement is relatively accurate and precise if you start measuring the matrix potential over about 90 centimeter or 1 meter. I don't know if now things are clear. Again, it depends on the accuracy of the measurement. The factory warn you that the measurement accuracy is not good enough if you want to measure the matrix pressure head when the soil is too wet. Paolo, any feedback?
No.
Okay. Again, let's talk a little bit again about the importance on the difference. Again, I want to stress you once more the importance of water and of course water and solute that move into the soil, vegetation, atmosphere depends on the differences of the total water potential. And again, for example, this is an exercise, I remind you, is a sort of a sum up of our lecture, the total water potential, you have the gravitational potential, you have the osmotic potential, you have the matrix pressure potential, and then in this tree that you can see the split of the different components of the total water potential among the pressure potential, osmotic potential, and gravitational potential. And again, this gives you the accurate idea, the very important idea that water can move from the higher total water potential to the lower total water potential. That means that minus 0.3 is higher than minus 0.5 minus 95.2 in water potential. And again, and want to close with I want to conclude this talk on water potential, just showing that these very interesting pictures from a paper. And you can see on your left the classic way that water moves from the soil to the root into the trunk and then toward the leaves and then transpirate in the atmosphere. But there could be also situation in a scenario B in the center of this picture that the humidity, the air humidity, just make water entering into the leaves and water just move in the canopy of the trees. But water can still move from the soil to the trunk. So there is a certain situation where you have that water from the top just encounter or just meet the water coming from below. And then there is this scenario C on the right of this picture. This is very interesting. This is very interesting. For example, even in the very dry environment, you have water that exiting. This is exiting from the roots. And again, because everything is governed by the difference in total potential, and in a very dry situation, you can have that the soil, the uppermost part of the soil profile is so dry that the water potential into the trees is higher than the water potential, the total water potential into the soil. So there is the water that can exiting the roots. And so I have this is the last slide that I expect on especially on scenario C. I expect that somebody from the audience make a comment on scenario C. Is there anybody that make a comment on scenario C? I really appreciate if somebody would comment on this scenario. As I told you, this scenario is typical of very arid environments, but
Daniel says that
yes.
It leads to plant wilting.
Oh yes. So well, there is water that vapor water from the atmosphere can still maintain some humidity into the plant, but again, this is the comment is interesting because this gives me the opportunity just to criticize the permanent wilting point. Because you measure the permanent wilting point considering the soil, but actually maybe the plant is the vegetation has enough water, so the vegetation does not wilt, even though the matrix potential in the soil get the famous 15 bars of permanent wilting point. So, but this is another story. This is all another story. This is all another criticism on about the permanent wilting point and field capacity. Actually, not. I expect someone make a comment about scenario C. Otherwise, I can give you a hint.
No. There are other feedbacks. My question about scenario C is that does it increase the soil moisture as well? Then Amor says natural water harvesting. And then Isai said, is this behavior controlled by plant physiology?
Uh, yes, in a certain way, Amos, thank you for this question. Yeah, you're right. The plant physiology can accommodate things, but I'm provoke. I would like to make a provocation. I won't provoke you about the scenario C, about the fact that actually water can exiting the roots. You see the blue arrow in scenario C, the blue arrow in the arrow in the soil just give us the idea that water is there is an exudation, as the plant physiologists used to say. And I am wondering, and I would like to have your opinion. Is this something that happen all the time?
It it happens when vapor pressure deficit is really low. From Philippe.
Yes, Felipe, you are right, but there could be something that prevent this phenomenon in the sense that in scenario C, you have water that enter from the atmosphere, then go into the field, then get into the tree, and then get the root. But I am asking you all: do you really think that always everything is governed by the difference of total potential? So I asking you all, do you really think that all the time when there is a difference in total potential from the root to the soil, the water exit goes out the root?
Kamat says that perhaps presence of solutes can prevent it, as in arid regions we also observe salinization.
Yes, but this is something that happen into the soil. But I'm wondering, I am asking if you think what happen when the water get the root and try to exit. So my question again, I try to put my question again in another way. Do you really think that all the time water can exit the root, or there could be something that prevent the exudation, so prevent the water to goes out from the root?
Is it a mean to stock water in the roots like potatoes?
Actually not. No, no. The answer is that I don't know if you think about the mycorrhiza. Usually the roots are covered by fungi, and these fungi not only sometimes make the entering of water a very difficult way to go from the soil to the root, but usually the plant is so nice, is so good that generate a suction into the vegetation, into the root, so water can enter into the root, and the water wins the resistance in the root tissue. But the mycorrhiza, the fungi that in most of the cases are around the root, can prevent the water to exit from the root to the soil, because the difference in the total energy is relatively low. As you can see in the scenario C, you have minus 0.8 and minus 0.7. So the the difference is relatively low, and the presence of mycorrhiza can prevent this, so the water just remain in a certain way blocked into the roots. And this is my last comment, just to so you can think about the complexity of water movement from soil, vegetation, and atmosphere. So, if there are no other comment or question, I suggest Paolo to have another 15 minutes break, and then we talk about the flow equation.
Okay, in the meantime, Nunzio, I'm going to share the screen just to show, I'm going to share a questionnaire for the participants in order to organize a potential summer school. So I leave, if you, I'll ask kindly if all participants can fill the questionnaire. It's very fast. So
Okay, Paolo,
the
sorry,
question,
just a
yes.
bit. We will reconvene at 4:15. Okay,
Okay,
Paolo.
okay. 4:15. Okay.
4:15. Okay, thank you.
Nunzio, actually, there was another question on scenario C. Just to reply quickly. In scenario C, can we include hydraulic redistribution? The plants can control in part water movement also by opening and closing the stomata.
Oh, good question. Of course, I maintain my comment in a very simple way, but of course, the stomatal control is very important, and especially when you want to model the stress condition into the vegetation, the stomatal control is really important. Another point that could be clear after the first part of the seminar, that the plant vegetation, can wilt even if there is enough water into the soil. Again, I want to make this point very clear. The plant can wilt even if there is enough water into the soil profile. If, for example, your tensiometer say that you are over the 15 bars, there is enough water, 3,000 bars or 3 bars or so on. Why plant can wilt even if there is enough water into the soil? But because it depends on the atmosphere. If, for example, there is wind or there is an atmospheric control, and the leaves, the stomata close to prevent water to exit, but they close until a certain point. They cannot go over, and so the plant start losing water even if there is enough water, and soil cannot feed water to the plant depending on the amount of water that the atmosphere requires. This is another important point in the soil hydrology and in the functioning of the soil vegetation atmosphere system. Okay, Paolo, if there are
no more questions.
Okay, no more questions. So we have now the second part, and the second part now refers to the movement of water. So we have now there is a sort of the concept of a soil water content, the concept of the soil water potential now merge in the concept of movement of water, not only in the soil, of course, like in this slide, but in general, the movement of water and solute in the soil vegetation atmosphere system. So to describe this kind of movement, you need, and this is a general statement, you need the equation of motion that give you the condition, the dynamic equilibrium in every point of the system, but you need the continuity equation that reflect the principle of a mass conservation, but you also need the equation of state that give the dependence of density on temperature, solute concentration, pressure values, and etc. But in most of the practical application, the equation of state is very simple. Is the density of water is constant. And of course, as somebody make a comment, of course, if this is not the case, if you are in situation in your modeling that you have many different temperatures, of course you have to consider the variation, the change in water density because of the temperature. But of course, if the salinity of the solid concentration in your system vary in relatively large intervals, you have to consider the changes in density because of the salt concentration, the solid concentration. But let's in the following we will consider the constant density of water, and we concentrate on the equation of motion and the continuity equation. So to understand the flow equation, let's start from the Darcy's experiment. Henri Darcy, in the middle of 19th century, just had the contract from the city of Dijon in France to make the fountains and to have some nice movement of water into the fountains. And he developed a way to make different jump of water, or to have water at different elevation and so on. And he doesn't consider the flow of water into the soil, but he only wants to generate some resistance into the tube to have a different elevation of water, or different to make some game with water. So on the right you see the original picture in the original paper made by Darcy. He made a lot of experiments, but he put sand in a vertical cylinders, steel cylinders, and he feed this cylinder with water from the top, and the water moved into the cylinder, sort of filtration of water to the bottom boundary, and the water moves because we have the different energy. Which energy? The H1 is the total energy, the gravity and potential pressure, pressure potential and gravitational potential, and the sum is the total is H1. And of course, in order for water to move from top to down, the total potential at the bottom of this cylinder was H2 is lower than H2 is less than H1. He made a lot of experiments with different kind of potentials, different flow of water, but he realized that the rate of flow, so the volume per unit time, divided by the cross section, the entire cross section area, was proportional to the ratio between the two water potential, H1 and H2, divided by the length of this column or these cylinders. And for those of you who have some basic of hydraulics, or even for the Fourier equation of the movement of a temperature, the flow of temperature in a bar, in a metallic bar, you have that the ratio between the rate of flow and the cross-sectional area is the specific flow Q, and the ratio between the difference in water potential and the length of the column is the hydraulic gradient, that usually we put the J symbol. And he eliminate the equivalence with equal, and we have the K. that is well known as the hydraulic conductivity of the sand material. Of course, this is a general equation, not only, and there could be also many demonstration of this equation. I mean, even if the the sand filter is not vertical, but is in a lateral tilting condition, the situation, of course, is the same in terms of movement of water from the higher water potential to the lower water potential. So we always have that the Q, the flow rate is proportional to the unit loss of energy, so delta H on L, and this proportionality is the hydraulic conductivity. To be precise, this the saturated hydraulic conductivity at the minus sign means that the flow of water is only in the opposite direction of the positive direction of the axis of the cylinder. So it's only a matter of the opposite sign of the two axes. But what is important that the flux is proportional by a property of the system. The hydraulic conductivity at saturation depends on the gradient of the hydraulic gradient. Is completely similar, and I am sure that all of you knows the Fourier equation of the transmission of temperature. The same equation, the flow temperature depends on the difference in temperature at the extreme of a bar. What is interesting is that what this equation said this equation say that there is a linear relationship between the flow of water and the gradient of the energy, and this equation this equation is a linear equation, and we can put this we can plot this on a graph. If we put the hydraulic gradient in the x-axis and the specific discharge in the vertical axis, we have the measuring point, and that you can interpolate in with the linear, and the slope of this linear the slope of this line is just the hydraulic conductivity, and this is a way to measure the saturated hydraulic conductivity in a porous system, and this is what we do in our lab in a certain way. We just reproduce the Darcy's experiment. But I want to discuss, this is relatively simple. You can find this in a lot of textbook, but I want to discuss a little bit with you about the intimate meaning of the specific flow rate, the specific discharge, because if you look at the dimension of the specific flow rate Q, the dimension are the discharge, so cubic meter per time, cubic meter per second, for example, over the area, so square length. And if you just arrange this, you have the ratio of length over time. But these are the dimension of velocity. So people can think that the specific flow rate is a velocity. But actually this is not. This is incorrect to say that this is the velocity of water into the soil. Why? The reason of this is that Q is the volumetric flow rate. The volumetric flow rate divided the entire cross-section area, but this is not the real case, because the cylinder has the sand, and the sand, there are the sand particles. So only not the entire cross-section area is occupied by voids. So the water cannot flow like a tube, like the pipeline that transfer water in your home, but only part of this cross-section area can be water can pass through this area. So actually, this give you only a rough idea of the velocity of water in the soil, and actually it's important to recognize that this is a specific flow rate and not an actual velocity of water into the soil pore. So this is the Darcy's equation. This is the equation of motion, and then we have to couple this equation with the continuity equation. To understand the continuity equation, I will make this very, very simple. But to make this, we can consider a very small cube into the soil system. So we have the porosity, we have the particles, the area. This small cube has the side delta x, delta epsilon, and delta z, and the area of this cube is delta x by delta epsilon, and the volume W is delta x, delta epsilon, delta zeta. So what we have here, let's make this very easy only in the vertical direction, but we can say the similar thing in the other two directions, the x direction and the epsilon direction, and we have a flow moving from below upward, and then this water enter in this control cube, control volume, and then there is water that exit. So we have again the specific flow rate, the green arrow, that so means the water that enter the control volume, and then after a certain time we have Q plus delta Q, some water that can exit. Actually, we should keep in mind that delta Q is can have a different sign. Delta Q can be zero. That means that the amount of water that enter the control volume is completely equal, is exactly equal to the water that exit the control volume. But again, delta Q can be positive. That means that there is more water that goes out from the control volume. But again, we have delta Q negative. What means if delta Q is negative? That some water of the water that has entered in the control volume remained into the system. So the net situation is that the difference between the specific flow rate exiting the control volume and the flow rate entering the control volume. But again, we have to compare similar things. So we should consider not the specific flow rate, but the volume. So we have to multiply the specific flow rate Q, or Q plus delta Q, by the area, delta x, delta epsilon, if we consider the entering and the exiting of water in the vertical direction. But this is the volume, the discharge, so the volume per unit time. So we have also to multiply this by delta T. So delta T is the interval of time that require water to enter and to exit, exiting from this control volume. So if there is water, so what we have again in the animation, we have the green arrow, the water entering in the control volume. Then we have the red arrow, the water exiting. It depends if there is water that remain or not, does not remain into the control volume. That this means that in this change of water into the control volume, this means that there is a change in the saltwater content, what we last time have addressed with the theta Greek symbol. So, and of course, there should be a continuity in this, and there is the conservation of mass or the concentration of this equation should give us a continuity of volume in the same mass or volume for water is in practical way is the same. So means that the first term should be equal, but with the opposite sign, the variation of the soil water content in the volume. I remind you that we have defined the soil water content and the volume of water on the volume of the entire soil. So this is why we have to multiply delta theta by delta x, delta epsilon, and delta t. Delta t because this is the situation that we have the variation of soil water content in the same time interval. So if we arrange things, we have that we can have that delta theta over delta t, so the variation of soil water content with time should be equal and with opposite sign to the variation of the flow in the vertical direction. And we can also write this equation in terms of a partial differential partial derivative. Why? Because actually we should write this equation not only in the vertical direction z, but also in the x direction and in the epsilon direction. And if we only want to consider this in the vertical direction, from the mathematical point of view, we have to write the derivative in terms of a partial derivative. But I don't want to go in more detail in this, but I only put this in this slide because you can find this on some textbook. So this is the continuity equation. As I told you, I don't want to go in more detail on this, but if you look and you can do again this game. The game is to see that the water enter in the box in this cube, and then there is some water that can exit, but only cannot exit. But this means that the variation of flux means a variation of the water content in this control volume. And here we have here an exercise that Paolo passed me. This is very simple. mass balance equation. We have soil, we have 10 centimeter soil cylinder. We have at the initial time, time zero, we have the water content into this cylinder of 0.3 cubic meter of a cubic meter. And we have a flux entering from the top of 0.05 meter per hour, and negative because it's opposite to the vertical Z oriented upward. And then there is some water that goes out this volume, and we measure this flow rate, and the flow rate is 0.04 meter per hour. And what we have to do is to apply the continuity equation that you can see on the right, and we can obtain from this equation the variation of the water content that depends on the variation of the specific flow rate and the time that we are considering, because we would like to know what happened after 0.5 hour, half an hour. And it's relatively easy to transform the gradient in differences. So we have the water content at the final time, at time t1, depends on the water content, the initial water content at the time 0, and minus the term that we have on the right. And we can now move to the values, and we have the initial water content is 0.3, and then if we put the variation over time, delta t is 0.5 minus 0, so it's 0.5, and then Q in and Q out are at the numerator of the ratio, and then delta zeta is the length of the column, 0.1. So this we obtain using this very simple exercise. We obtain 0.35 cubic meter over cubic meter. That means that the because of the movement of water from top to down, we have an increase after half an hour, an increase of saltwater content from 0.3 to 0.35. So this is a very simple exercise, an application of the continuity equation. I remind you. Yes,
sorry.
Yes.
I want to take the chance to specify that this is an exercise from UC Davis, credits from Jan Hoffmans. That is another big guy in soil science. So this was during my time in UC Davis. I thank also Jan Hoffmans for that. Thank you.
No. Yes, good point, because Jan is a very good friend of us, both of us. And yes, this came from Paolo and Jan. So, and I hope that this very simple exercise give you an idea of the continuity equation, and just give you an idea that we does not consider mass, because we, again, as I told at the beginning, we use the water in very practical application, and we consider the density of water is quite constant in our exercise. So this is why we can move from mass to the volume, and we consider the volume. And let's move to the richest equation, that because this equation is applied in a saturated condition, but under unsaturated condition, we have to combine the flow equation with the continuity equation. So this is the continuity equation, and if we put in this equation the Darcy's equation, the flux equation, considering the hydraulic conductivity and the unsaturated condition, we have this is in a very easy way. We have this again. We have here the partial derivatives because I am writing this equation only for vertical, the vertical situation. This is a 1D equation for in the vertical direction, but actually you have the flow even in the other two direction. But also we discussed the last time that in most of the practical application, especially those involving the balance of the vegetation, soil vegetation, water balance, most of the flow can be considered that happen only in the vertical direction. Of course, this is an approximation. So again, is the matter of uncertainty, is the matter of how accuracy are your calculations. So if we oriented the vertical direction upward, we have this equation. And if we, in most textbook, the derivative of water content over metric head is the C, the capacity, the retention capacity, and you have this equation of the well-known Richards equation. I have to say that this equation is written in this way with the plus term at the extreme right of this equation. Why? Because the vertical direction is oriented upward. But you can do this even if you orient the vertical direction downward, because people sometimes prefer to have the reference at the soil surface, so the vertical direction is oriented downward. In this way, the equation, of course, does not change, remain the same, but you have to change the last sign, not plus, but minus. But I want to stress a couple of things. And discuss with you some important things. What are the independent variables? The independent variables in the Richards equation are the position, Z, and the time. So these are the variables, the independent variables. Any equation has independent and dependent variables.
Nunzio, sorry, there is a question.
Yes.
From Amor, please explain why Q is negative.
Where Q is negative again in the Darcy's equation is only a matter of is an agreement. An agreement is a convention because the flow of water is opposite to the direction of the cross-sectional area. And I have to go, sorry, I have to go again here. Okay, this is the explain. For there is an agreement that the axis of normal to the cross-sectional area is opposite to the blue arrow over Q. So this is why this is a minus sign. Okay. So things works that way. But of course, the minus sign, as you know, Amor, in any analytical equation, the minus sign has a physical meaning. The physical meaning of the minus sign is that the flow is opposite to the gradient of the flow. and or the gradient of the pressure potential. So, and it depends on the positive axis that you fix when you compute the gradient and the computation of the gradient. The gradient here in this equation is delta H on L has a mathematical rule. So if you have to follow the mathematical rule to compute the derivative. This is a mathematical rule. So just to be consistent with the physical things, we have to put the minus sign just to be sure and to explain, to give to this analytical equation a physical meaning. The physical meaning is that the flow is in the sense opposite to the gradient, the derivative of the total potential. This is something of mathematics and is important. Again, like here, like the continuity equation. The continuity equation, you have fixed the positive orientation of the x, y, and z axis. And to be consistent with the physical meaning, we have to use the minus sign. I hope that this explain things. And this is why in this equation, if you orient the vertical direction downward, you have to put the minus sign. And if you put the minus sign, this means that the plus sign in the extreme right hand of the equation became negative. But again, I want to spend time with you. It's important to understand the physical meaning. This is what I am more interested in this moment, is to understand the physical meaning of the Richards equation. We have independent variables. The independent variables are the position of the water at what time the water is at the position Z. And what is the dependent variable? The dependent variable is the metric potential. So this equation gives you the metric potential at a certain location Z at a certain time T. But this depends on the type of soil. So what are the soil parameters in this equation? The soil parameters are the hydraulic conductivity, K, that depends on the metric potential, and the term C, as I mentioned before, the capacity, the retention capacity of the soil is the derivative of the water content of the metric potential. And this again, as you can see, the two box, the green box and the other box that delimitate the two soil parameters that we call the soil hydraulic properties. These are the soil hydraulic properties, and on the left, this water retention function. This function relates the water content with the metric pressure head. I remind you, the metric pressure head is the metric potential referred to the weight of water. This is why expressed in centimeter in the length. And also, it's also interesting to see that this function is strongly dependent on soil texture. We have the blue pattern of a sandy soil, but you have the red pattern of a typical fine textured soil like a clay loam soil. On the right, you have the corresponding hydraulic conductivity function, and again, we have the pattern of sandy soil is the blue line, whereas the red line is the typical hydraulic conductivity of a fine textured soil. Of course, these are only schematic, but give you an idea of the importance of soil texture, but also of soil other properties of soil, like the arrangement of the soil particles, what we have called the structure of a soil. So the texture and the structure of the soil are very important information to understand the pattern of soil water, the soil hydraulic properties. And you can see that so how the water content and the hydraulic conductivity changes as the matrix potential changes. And you can understand the saltwater function if you remember what we have done at the beginning of this talk, the capillary tube model. We consider the soil, the model of the soil is the bundle of different capillary tubes, and different capillary tubes, so capillary tubes of different diameters, they have different capillary rise, different elevation of water into the tube, and this means that the amount of water that the soil can retain is different depending on the distribution of this bundle of capillary tubes. So this is a very simple explanation of the pattern of the saltwater retention curve from saturation condition to the dry condition. But I can show you a real measurement, actual measurement of water retention function that we did in my lab with a very accurate equipment. It's the gamma ray attenuation method, and you can see this is a quite homogeneous soil. We have measurement at 3 different depths in a soil core of 15 centimeter height, but you can see that there are even small differences, but you can interpolate these, and Paolo on Monday will show you the most used relations that you can employ to interpolate the data points. But another situation that, but there is no time to go into this, is the fact that especially in sandy soil have the phenomenon of hysteresis, in the sense that the relationship between water content and pressure, matrix pressure head, depends if you are drying the soil or if you are wetting the soil. But this usually is neglected in practical application, or you can consider only if your soil is a real sandy soil, or if there are infiltration and redistribution processes that require to have this information. But I also, I'm very happy to show you that a very precise laboratory experiments can highlight this phenomena. And then the last slide referred to the hydraulic conductivity. This is the hydraulic conductivity. The black triangle on the right is the measured saturated hydraulic conductivity. Of course, the data on the hydraulic conductivity are more scattered, but again, you can use different interpolation relationships that help you to have this data point just put on analytical relation, and then use this relation in the richest equation in the model. Okay, Paolo, I think I am in time, just 4:59, so just 1 minute. And I conclude this lecture. I understand that this lecture can have been a little bit heavy because of mathematics, because of physics, but I hope that you appreciate the importance to understand how important it is to consider the flow of water in terms of differences in total water potential, and then also to consider how important are the soil hydraulic properties, and to obtain information on soil hydraulic properties to model in in a more comprehensive way the movement of water from soil to the vegetation. Okay, Paolo, any questions or comments?
Thank you very much, Nunzio, for this wonderful